Thank you. So welcome everybody again to Colloquim. Have you ever wanted to have a helicopter? I have it on good authority that if you listen carefully to this talk, you will learn, from the master of having a helicopter in the LTI. That is Alex Waibel, our speaker for today. He is a pioneer in multiple different areas of language technology research. He's a professor at the LTI and also at Karlsruhe Institute of Technology in Karlsruhe, Germany. He will talk to you today about what research is, or answer the question, what is research? So, thanks so much.
Okay, so I don't know what we did to the wiring that it doesn't come out, but normally you all have seen captioning on under Zoom calls, right? I trust. And you can turn it on in multiple languages now, and Zoom now has a feature that lets you also translate between the different languages. So you can speak in German or English, and it comes out in Chinese or French or something. Right now it works between, somebody's not muted. Anyway. Now that feature comes from us. We have, I will tell you in a moment, it's a long, long story of where we started with speech translation years ago, and recognized speech, and I'll tell you a little bit more about this. But it gets into this whole story, what is really research and why do we do it? And you're all coming here into the LTI in order to learn something about graduate studies, but you really don't know what it is yet because you've explored the gym and you met new friends and you settled in and you're getting ready for the semester, you signed up for courses, but there's this confusion. Everybody talks so intensely about research and you wonder what this is, because for many of you, that's new. Many of you, who comes directly from a bachelor program? Who came from a master program before? And the rest of you came from industry? Okay, so we really have a mix of things, but something attracted you to become a scientist and to go to Carnegie Mellon, one of the top places in AI, to learn something about research, hopefully. But the question is, why do it? It's 4 or 5 years out of your life, and taking courses you could be doing online. So what's the advantage of coming to Carnegie Mellon? And I would claim it is this research, and you hear a lot about, everybody talks about research, and so it's an important thing, what it is actually, and how we define it, and why we make a big deal of it, and what the particular Carnegie Mellon view of it is. Now, what are you here for is, primarily say, well, let's get a PhD and let's get rich, let's become scientists, and let's get an education. I don't know in which order of priority you're defining these things. But they all have something to do with getting an education and becoming a good scientist. And so if you look up what does it actually mean to do education and research, education, Nico Habermann was one of the founding fathers here of the School of Computer Science. He once told me that education is gaining knowledge, understanding, and skills. And so what's the difference between these things? Knowledge, understanding, and skills. So let's drill down a little bit and look at this and saying, well, when you take courses, and the first part of your graduate studies is to take courses, there you learn known facts. So you basically review what people have done before you, and you learn this from textbooks, from research papers, and so on. And that's factual knowledge that gives you the background to really base your investigation on. And then research is where you address the unknown and solving new problems. That's why it's a bit ill-defined, and you will increasingly, as you go on, go more into this unknown area where nobody really knows exactly where you're going, because it's research, it's open. And so this requires, of course, as a background, reading the scientific literature so that you don't reinvent the wheel and begin with things that are already known. And then you experiment a lot. A lot of this is experimentation because we're getting into new areas where nobody really knows. And then you implement, you're building actually things and not just kind of philosophizing. And that means you're developing things also, and that requires skills. So skills on how do you do experimentation, how do you do development, how do you do coding, how do you implement something. And so that's the second leg on which we stand in this type of education. And then what is understanding? Understanding is perhaps the weirdest one of them, because when do you understand something, right? But it's crucial because it develops a sense of direction. How do you pick your problems? How do you find possible solutions and approaches? How do you get a sense for the problem? And all of that comes from a deep understanding which grows, which is something that you acquire over time. So in your experience, most of you have come from an undergraduate. The difference is that you, in some sense, you do a lot of coursework and homework sets, and they differ in the way that they're very scheduled. You know, you have to hand in the homework set a week from now. There's a fixed deadline, and there's a known outcome. You know that you are either correct or not correct, and you get the grade based on whether you get this correct or not. And then you were told what to do next. Now, graduate students, that's only part of what you do. It's part of what you do is to do these homework sets and things, and particularly in the beginning, to acquire this knowledge and learn about it. But the research, when it becomes the dominant part, is much more ill-defined. You don't really know, and there's usually not a perfect solution or perfect answer, and you don't really necessarily know whether there is a correct answer or even an answer at all. So it's more ill-defined than your homework sets that you're used to. And so we gradually grow you into this, or you gradually grow into this by beginning with your master program, and this is typically 50% research and 50% is your homeworks and your studies, of an 80-hour week. We say that jokingly, of course, because normally for most normal people the week is 40 hours, but obviously when you're a researcher you spend a lot more time on it. So eventually your master's, your PhD thesis is 100% of the time, the research part of it. And so gradually you take less courses and become more involved in the research agenda. And so building that ability to do research becomes increasingly important. So we generally actually don't want students to do, many students say, oh, let me get the courses out of the way and I'll just spend 1 year only doing courses and then the next year only research. It doesn't work that way. You need to really begin early on to hone your research skills, and that's what we'll be talking about today, how to do that while you're actually taking courses, and it takes time to attend to those courses as well. Research is, other than why we're here and getting a PhD and it being an interesting pursuit, it's also, for most of you, a way to earn your keep in a way, because graduate studies here are expensive. We'll talk about money in a moment. But work for your graduate student support is part of this, and so that's one more reason why actually research become an important element of it. Now, what exactly is it? And so we will want to drill down a little bit in what research is. And if you look in the dictionary, you find as a definition, scholarly or scientific investigation or inquiry, close and careful study, to study thoroughly so as to present in a detailed, accurate manner, research, diligently inquiry or examination in seeking facts or principles, laborious or continuous search after truth, as researchers of human wisdom. So there you have it as a definition. The thing that all of these different definitions have in common is that they take hard work. They're not easy. So they take repetition, they take intense investigation, and that means it will take time and effort. Now, in the graduate program, research leads to publications, leads to a PhD, and gets you paid. So we need to talk about these through different areas because they're all actually important, because publishing is really ultimately the main outcome and the main product that we're doing is because we generate ideas in research. We don't necessarily develop products at a university. So your ideas have to have impact. And so publishing, communicating, and so on is a big element. We'll talk about it. Getting a PhD, there's a whole set of things involved with that. How do you get a PhD? What are the phases and how do you prepare for it? And then what do I do to get paid? You know, I mean, that's after all also the reality of life. So how do you go about in the graduate program? First of all, there's the question, how do you pick a research project? Most of you have to pick an advisor. Most of you have to discuss with your advisor what the research is that you're going to do. And since it is an open-ended problem, or we do research on things that are new and unknown, picking a project is really the first step, and that's so important in this whole process. And the CMU style of picking research projects is you could, out of the whole world of interesting things you could look at, why not look at the problems that are actually useful ones, right? So you can spend a lifetime investigating, and there are researchers in this world, academics, who work on problems that nobody really cares about. And there are some sciences, and I will not go into details so I don't offend my colleagues in other fields, but there are some scientific endeavors where there's only 2 scientists in the world who care about it, and they publish and reference each other, and they build a whole career out of the references from each other, etc., but nobody really cares. The CMU approach is to pick a practical problem that may change the world, but it's still too wild and crazy that it's, there's no solution. No company would dare doing it because, you have to invest in it and nobody knows whether it's possible even. And it was formulated in a way by another one of the founding fathers of the School of Computer Science, Alan Newell, one of the icons of AI and of Carnegie Mellon, who said there's no science without a system. So doing science really requires having a practical view or a practical goal in mind, and instantiating this in a system is your best way to actually see whether your science is on track, and this is what we'll also look a little bit at. So your motivation is a real problem, and it offers real problems offer real problems. So if you pick a crazy far-out problem saying, moon landing, etc., and some of you have heard of this organization DARPA, the Defense Advanced Research Project Agency in the United States. DARPA has been unique in pushing these kinds of practical problems also. And if you look at what they have produced over time, it's the internet, it's GPS, it's stealth, it is personal computers, it's machine translation. DARPA has had a hand in all of these different things and has provided a great deal of funding to Carnegie Mellon, and Carnegie Mellon really resonates very well with this practical approach because we address these far-out things. Imagine you're back in, when I was a student I came to the United States from Germany, and that's another story I'll tell you in a moment, but when I came to MIT, I wrote my mother letters. There was no email, right? I put them wrote them by hand, put them in an envelope, and 2 weeks later, she would get a letter from her son. Now, this is insane in today's world. I mean, you all grow up in, my kids already, when they go to my little one, when he goes to the television set, he went, as a 2-year-old, he went to the television set and did like this, and nothing happened on the television set, and he was surprised because his iPhone was doing this. You could just swipe, and you could do email and texting, etc. But we lived in a world where there was no email and no internet, and this is only in one generation. I still stand here telling you these stories. And so we created a totally different way of running the world. And these were done by programs that had really began with a practical vision. Can we build an internet? Can we build an infrastructure that makes this happen? Now, this happened just within my generation. And if you imagine when you go out into the real world and spend a 40, 50-year career, what will the world look like at that point? What are the crazy problems of your generation that are worthwhile to solve? Now, practical problems not only pose real problems, hard problems, but they also give you a way of estimating or getting impact. I mean, it's good to have impact. If you're sort of one of those two scientists that references each other, it's kind of lonely, right? But if you do something where suddenly if you have success, you have impact, other people are doing it, industry is picking it up, television crews come and want to hear about it, you're moving the needle, you're making an impact in society. And I remember that was, to me, an important thing as a student, that I wanted to not to do something that I thought was fun and interesting and curious, but also something where I can help the world and have some positive impact. The other problem of practical problems is they give you a way to measure. You improve what you measure, is what several people have been known to be quoted. And that means if you can have a goal in mind, says, I want to reach this, we can usually define metrics. And if we define metrics, we can measure whether we're on the right track. There's entire sciences that get lost in the weeds because they wind up pursuing something that you can do a lot of introspection and have interesting discussion with your friends, but you're not really sure whether you're making progress, because if it's just introspective, you could fool yourself. And the history of science is full of science that completely get lost in something that later on becomes useless or uninteresting. Why? Because they don't measure. They don't have a clear goal in mind. They don't measure their impact and see whether success is actually being achieved. And it makes it objective rather than somehow being subjective and saying, I'm interested in X, Y, Z. We have really a measure to tell us whether we're making progress and whether what we're doing is even correct, right? And measurements do that, and then we can compare with our friends and colleagues and so on, and we can really see whether we can make progress. Success can be enjoyed if you then achieve a good result, you get better improvements and get better results, then and TV comes and whatnot, and the internet takes notice and whatnot, then that success can also be enjoyed, but it also comes from the fact of making a contribution to what people care about. Now I always like to view this in this plot. It's a bit of a fake plot. As you know, there's no units on this graph, but it's more or less the way often scientific development goes, that where you begin with something that is totally abstract and different from practical problems. And it's just if you worry about the first picoseconds of the universe, right? It's interesting, but it still doesn't really resonate with the rest of the world. And if you draw it out like this, where you look at the applicability and how close it becomes to products, and on the other side, the amount of resources devoted to a task, how many people are really interested in pouring money into it, then most of the exciting areas and the areas that we really care about at CMU is where we start with really crazy ideas here, and then really spend some time working on them and hopefully move them in the direction where we just say, wow, this really actually works, and this is an interesting new way of doing things. And at that point, of course, as a university, we tend to disengage, because then it becomes product-oriented, and then we pass it over to transition. Now, transition happens when ideas mature, and a university is not equipped to build your next iPhone, right? I mean, that's better left to Apple, because they have a huge organization. But if you're back in a world where there were no iPhones to even look at that, I have colleagues who invented the wireless chips in the iPhone, or people who did the algorithms around some of the things you see in these practical applications. When it's not known and you have never really seen it, then doing this type of initial research and development to demonstrate that it works is really the cool thing, and then you let industry and others run with it. Now, this thing is overlooking, of course, a lot more detail, because transition also has different aspects. How do you transition? And we'll talk about this. You can publish papers, but the other way is to also collaborate with industry or government to see whether what you built can be transitioned into something. Or another model, which is particularly strong in the United States, is that you go into a startup company, or you transition this in a startup company, because a small startup company is much more able to take an idea and take a risk, and they may fail. Many or most startup companies actually fail, But you take the risk and you develop something and see whether this can actually work as a product. And if it works, often it gets transitioned either by the company going IPO and become a huge new industry, or it transitions by getting acquired by a large company that takes it up and then puts it into their product line. And that all happens. And we actually, I taught a whole course on entrepreneurship where we really looked and invited various success stories from Carnegie Mellon where people have done this, where they began with something really crazy and then ended up with something that defines industry. And if you look at these companies that are out there, Apple, Google, Facebook, they all don't exist very long. I mean, they were all basically companies. Facebook was started in 2000, went IPO, I think 2012 or 13, right? So this is not a long time ago. This is just 10 years ago. And this pops up so quickly now that you will experience this in many ways. And so this road of doing startup companies and seeing whether you can be part of that transition really is a fascinating aspect of that. Now I digress a little bit, and I'll go through these slides very quickly because I don't want to make this talk about Alex Waibel, but more about what you need to learn and what your story will be. But it just gives you a little bit of an idea of what my trajectory was. And my crazy idea in my life was in 1978. It's been a while. I said to my MIT advisor, I came from Germany as a student, and I was intrigued by this project that they had at MIT to build a speaking machine for the blind, a talking machine that could take text and convert it into voice. And in '78, that was absolutely nuts, because how can you make a talking machine when we didn't have email at the time, right? So text or writing was the best we could do. And in fact, some of my first programming course was still on punch cards, and there were some people who actually had teletypes, which was really cool. And when I came to CMU, we had the first modem. I actually got a modem at home, so I could actually type stuff in from at home. But it all was very, very primitive still at the time. And when I said in 1978 to my advisor while we were working on speech synthesis, he says, hey, I want to build a machine where I can speak into it. It translates it into another language, and it comes out as speech on the other side, you know. Well, he looked at me and said, well, I was a bachelor student at the time, and he said, well, that sounds really great, Alex, but go back and finish this thing we have to do in our research lab. So he was fortunately polite enough to not just tell me I'm nuts, forget it, and so on, but he didn't discourage me. But he obviously also pushed a little bit of realism into my crazy idea by sending me back and stay focused on TTS, on text-to-speech synthesis. So don't forget your stupid ideas, your crazy ideas. At the same time, be practical. Make sure you make progress along the things, but keep your dreams. Because my dream didn't go away. You know, I said, well, this is our situation. We live in a global village. We have 6 billion phones. You can now connect anyone with anyone. There is unprecedented exchange in communication. In Europe, there is integration of 23 languages. They have human interpretation services, and so everyone needs to interact with different languages. The cultural diversity is enormous, 6,000 languages. We don't want to take this away from people. They won't, you know. Tell someone in China that they all should learn English. Would they do it? Probably not. Tell anyone in America to learn Chinese to communicate in the future. They wouldn't do it. They would stick with English. So it's impossible. Forget it, right? So we are going to live with this diversity of languages, and that diversity is good because it expresses our identity, our language, and our culture, and our pride and individualism. So the challenge is, how do we achieve integration and communication, understanding among people, despite the fact that we are separated by languages? So we began with this, and when I finished with my work at TTS at MIT, I said, well, to build a machine that allows us to communicate, I was in this little corner here to do text-to-speech synthesis in English only. And it dawned on me, well, we need automatic speech recognition, to convert speech into text, and then we need to have machine translation to convert text from one language to another, and then we have to do it all in the inverse direction. We have to do it with many languages. So slowly it dawned on me how hard that problem would really be, and I applied to Carnegie Mellon because at Carnegie Mellon there were people working on ASR and speech recognition. And so I wanted to be part of that. Nobody dreamed at the time to do machine translation. In general, people had given up on machine translation in the time. They said it's too hard, it's AI complete, can't do it, no way. So there was nobody doing machine translation, but not to be discouraged, I said, let me then focus on this corner and do automatic speech recognition. So I did my PhD on ASR, automatic speech recognition, but machine translation remained then also on the horizon, and I later would get my chance by going to Japan. Japan had an effort to restart research on machine translation, and then later we formed the Center for Machine Translation here at Carnegie Mellon, which then turned into the LTI, of which you are part of. So machine translation was that vision which was eventually accomplishing this first department in the United States that would devote itself to the study of machine translation. Now, why is it so hard? Languages, you know this, of course, but there are all these stories. The big problem, of course, which was not recognized in those times, was that language is enormously ambiguous. In those days, people thought we can just do it by rules. We write a parser with a bunch of rules, and then we'll convert it into another language, and voila, we have machine translation. But it was quickly discovered you would get crazy results because language is ambiguous. You have something like the spirit is willing, but the flesh is weak. Allegedly, this is folklore. It actually never happened, but the New Yorker wrote an article on it, and hence it became folklore and machine translation. Allegedly, it was translated into Russian, and from Russian back into English, and out was supposed to have come, the vodka is good, but the meat is rotten. And the reason why it's funny is because there was a misinterpretation of all the words. Spirit can be alcohol, but spirit can also be the mind. And this sentence comes from the Bible. The spirit is willing, but the flesh is weak, meaning our human weakness. But we're not talking about meat, and we're not talking about rotten meat, and we're not talking about vodka, right? So there's a philosophical interpretation of the same words that leads to this ambiguity. Ambiguity, though, in this whole interpretation problem goes much deeper. We have syntactic ambiguities, times like an arrow, 6 different parsers, right? You could say fruit flies like apples, right? And time flies like an arrow. So it's a different syntactic interpretation of the same sentence. And then, of course, in speech, in the acoustics, we have the same problem. You can say this machine can recognize speech, this machine can recognize speech. Give me a new display, give me a new display. You pronounce it exactly the same, but you would type it in different ways. How do we decide as human beings? We decide by intelligence, we say. But intelligence means we have a great deal of contextual experience. We know what the words mean in this particular context, so we can type them out correctly. So in German, for example, if you say, ich freue mich, dass Sie heute so zahlreich, I'm so happy that you have come. Sie means you, but it can also mean they. So if you say, if the baby does not like the milk, boil it, does that mean you're boiling the milk or you're boiling the baby? I hope we are all agreeing on boiling the milk, but how do we decide? We decide that by the context. You don't boil babies, but you boil milk. But if you translate it into German, you need to know that because you say, you koche die Milch, es or sie. You have to pick the different pronoun based on your decision on what you're referring to. This is, linguists call this the pronoun resolution problem, right? Am I right? Where are the linguists in the room? Okay. Human dialogue makes all of this even harder because human dialogues is never really syntactically correct. People mumble a great deal, and you don't really know what they say when they stutter in human speech, and they stutter around, but somehow we extract from it the essential meaning. So at the time, AI was just all rule-based, and people thought we could code this all into AI, into an artificial intelligence. But for me as a graduate student already at CMU, it seemed crazy to try to do all of that by rules. There's just so many facts you would have to code. We would never have a chance. So there were two friends of us at the time. You know, Kai-Fu Lee, a good friend, was beginning to do his PhD work, and I was working on PhD. I was getting intrigued. Jeff Hinton was at the time at Carnegie Mellon, and I was intrigued by neural networks already before Jeff came. I read about perceptrons and said, why is nobody looking at this? That's the way to go. We really need to look at learning machines. And so Kai-Fu went with statistical learning machines. I went with neural network learning machines. I then later developed this time delay neural network, which became the first convolutional neural network, which we applied successfully to speech. So we could really learn networks. And the thing that I found most intriguing about these networks is not only that they became great classifiers, but that they would learn hidden representations of something internally which I never have to code. So all the rules that I thought were impossible to all code would be invented by themselves through a very, very simple algorithm that would basically build those. And now we know this, of course. In those days, it was largely ignored. People thought this, we were called neural nuts, you know, people who just have these crazy ideas. But 20, 30 years later, with appropriate computing, we can do it now. And in fact, it has a great performance. So you will learn all of this in the studies. Let me just skip over this in interest of time. But back to the story of language. It's, of course, language not only in speech and text. Language also has many other manifestations. So if we want to really build successful communicators, we have all these other things: images, handwriting, lip reading, and so on. So it became really a complicated stories. Facial expressions, you've all seen those, and they all mean something. They all speak a language, and we need to interpret them. Now with neural networks, great jumps eventually. You know, we did this in 1987, but the time wasn't ready for it because neural networks require a lot of computing. It wasn't until we had GPUs and more memory and more data that people revisited neural networks with enormous gain. So machine translation made big jumps by neural networks, and so did speech recognition. Now, is it still an issue today? Yes, we still improve core technologies, speech, MT, and speech translation. We have to improve the user experience. That's very often forgotten. It's not only making better accuracies, better translation, but we need to somehow have a good user experience so that you can integrate these systems in the communication scenario. And then, of course, research on lifelong learning, which is really more for the future. Okay, back to how this developed for us at least. 1991, we built the first demo on a speech translator. It did 500-word vocabularies, wasn't particularly practical, but the world for the first time says, hey, you know, maybe we can do this, that we can speak into a machine and translate into another language. And that was exciting and generated news. It took another 10, 20 years before we could actually put this in a product. We started a company called Jibigo, and that company, we built speech translators on a phone, totally embedded, no cloud computing. This was on the phone, a full speech translator, 40,000 word vocabularies to do dialogues for tourists and medical professionals and people like that. Took 20 years to do this because the engineering had to be done, all the science on the statistical learning and machine learning had to be done. And then we were very lucky that this phone came out. It's the Apple 3GS, and it had enough oomph on it, enough power, that we could pack all of this, what we wanted to do, on a phone. Before that, it was just not enough power, and you could do only vocabulary lookup, et cetera, et cetera. So we had the great breakthrough in 2009 where we could pack this all, and Apple came out with the Apple Store, and I thought, in early 2009, I said, 3GS announced, they're doing the Apple Store. Wow, we can really finally do this. And we deployed it for human.
I took this amazing trip to Spain after college, and with my iPhone, I checked out hostels before booking them. Shared pictures as I went. My mom loved that. And I even downloaded this app. which became my personal translator. Where's the train station?
¿Dónde está la estación de tren?
All I really needed was my iPhone and my passport.
So we had no influence on this commercial. Apple just decided to do that. We had our app on the App Store, and so it was a big hit. You know, sales were through the roof, etc. And it was fantastic. Economist was writing about it, and eventually, of course, Google and others started to copy. That's the other thing. A story on innovators. You know, you recognize the pioneers by the arrows in their back, right? So if they do something good, you're going to have people shooting at you, and that happened to us too. We had a wonderful ride for a while, and then Google and Microsoft were basically, and I have lots of stories for some other day on how that went. So Facebook came and they needed something in language technology, and so they acquired the company and put all this language technology goodies in their products and so on. So it was a good outcome for us. So I went back to the university, and then the next stage for us was to build simultaneous lecture translation, because at the time we could only do individual sentences. And so here we wanted to do monologue, entire lectures like this one, translating. So what you're seeing right here, a lecture, can we transcribe it and translate it? So that was our next challenge, and we built this in 2005. We had a first press conference here at Carnegie Mellon where we showed that this was possible. And then in 2012, we rolled it out in Germany, because in Germany, with foreign students coming to a German university, many of them struggle with learning German. If the lecture is given in German and you come from China or US or somewhere, how do you deal with a lecture in German? Well, we built a automatic simultaneous interpreting system that would interpret these lectures into English from German, and then added gradually additional languages. And so it would look like that. Students would simply go to a website or to a, we still run this, by the way, it shouldn't talk in the past tense, it still runs at University of Karlsruhe Institute of Technology, where students can simply go to the website and they get simultaneous interpretation of the lecture into English. That was noticed by the European Parliament, and so we had some research grants where we could bring this to the Parliament, and then we had side-by-side human interpreters, right? And they're the best in the world, so it was scary because they don't want to have some techies come and say, oh, we take your job. But so we put this side-by-side, and they were puzzled by this, but at the same time relieved, because our system still made more errors than they would. And so they were happy that they still have a job for a while. But at the same time, they could see the potential of this type of technology, because as it was shown, this is the Rectors Conference in 2012 and 2014, where they started, and these good folks are all part of the Directorate of Interpretation. There was no hostility. There was a great deal of friendship. Why? Because with 23 languages in the European community, it became clear that even in the Parliament, they cannot do everything by human interpretation alone. It's just too big, 23 times 23 language directions, and then all these side conferences are happening. It's impossible to do it all by human effort. That's despite the fact that they're spending hundreds of millions of euros every year on human interpretation services. So it's more like a symbiosis. And so we became, this is the Secretary General, we became good friends with them, and we began to introduce this. I don't have time to give you examples of it, but again, the press has things. And we did a startup companies. Other universities wanted to have that too. So we did a startup company again called Kites, where we developed these systems to bring this to other universities. And then the pandemic hit just recently, and everybody went online. So of course our lecturing went online, and all of our automatic transcriptions and translations went online. And there was another company that became quite notable in the pandemic because of its video conferencing capabilities, Zoom, and they noticed our technology and acquired the company. So again, the Kites team, the startup company called Kites, became part of Zoom and got integrated into Zoom, and they're now building the captioning and the translation of Zoom services. So you can turn on your Zoom, and that's what I wanted to show you in the beginning. If you turn on the captioning in multiple languages. They support 10 languages. You can now get automatic transcript, and if you have the right product, also the translation. So there is some marketing involved here too. I think you have to pay $60 or something. I don't know. We're working on this with the CMU people to make sure they make that available to everyone. So that's amazing. You know, now we started with something totally crazy, and now everyone in the world can communicate with everyone in the world via Zoom and subtitling, or with handheld devices that they can travel with. And whether that's just done entirely by us, or whether our friends at Google and Microsoft and so on do it too, it doesn't ultimately matter. What matters is we connected the world, and we made the world a more closer space, a more understanding place by providing this in technology. Now, what are we up to now is we're building the crazy new thing, which is called lip translation. I'll play you a little bit, and then I get back to my original story.
Super, dann begrüße ich Sie ganz herzlich wieder zu unserer Vorlesung Kognitive Systeme.
This is difficult to hear, right?
Ja, mit dem tatsächlichen Stoff an. Ich bitte zunächst mal die paar Minuten Verspätung zu entschuldigen. Wir haben hier noch mit der Technik gekämpft.
You cannot hear that, can you?
Manchmal mit Brummen belegt sind. Aber ich hoffe, das wird so gehen, wie wir es jetzt gerade haben. Wenn es unterwegs irgendwie Geräusche gibt oder Brummen gibt, dann wird unser Team...
So I apologize. This is me giving an online lecture in German, as you might have heard a little bit, and this is in English.
Super, then I warmly welcome you again to our lecture on cognitive systems. We are starting today with the actual substance. I would like to apologize for the delay of a few minutes. We still fought with the technique here, because the microphones are sometimes covered with humming, but I hope that will happen.
Okay, so what are you looking at? We are doing speech translation with subtitles, which is now as a product in Zoom. And so what we're trying to do here is not only do speech translation, but what I call language transparency. You want to have a dialogue with someone else and not even notice anymore that they're speaking a different language, right? So we can create here a video experience of the other person speaking your language, meaning it gets translated. We manipulate the lips so that the lips move in the translated language, and the voice gets adapted back to my voice. So this is still my voice in English, even though I spoke in German. And we're now having experiments with Japanese and various other languages where you can really make the same speaker speak a language they don't know with their voice and their lip movement. And so this is our president in Germany, the president of the university in Germany, and we had him translated into different languages. And of course, there's ethical questions here too, because we made one video where he says he likes our research and he wants to pay us more money. But I only send it to him as a joke. But you can see there is issues with this, and we're working on that also. Okay, back to the story. What is your story, right? This was my story, right? And the question is, how do you do this? How do you succeed in becoming a scientist in your own right? As we said before, there is a couple of elements. One of them is communication, and it's really crucial in your research experience or in your research to communicate with other people, because initially it's all about the ideas, and you need to convince other people by ideas. And I still remember when I was a young scientist in Germany that there were some scientists who were so confusing in what they were explaining that nobody really understood what they were talking about, and then you get polite silence. And for many of them, that was the goal, because that says if you can't persuade, confuse, right? So if you don't have a good idea to tell, just tell something new, right? And but that's not what you should do as Carnegie Mellon students. You should have a good idea and a good story to tell, and then presenting it in such a way that you really convince others to adopt your idea. That's the goal. You want to be cited. You want to be quoted. You want your results to transition. So then learn how to give talks and lectures, how to debate and discuss, and how to write reports and how to write papers. And let me spend a few words on this. That means speaking skills and writing skills. And this is not going to be, that's part of the skills element of your education. And that's not going to come natural to many of you, because particularly if you're from a background where, you know, speaking up is not encouraged, right? Particularly not in front of famous people or bosses or whatever, right? Very often you're supposed to just be quiet and silent. But being in debate, in the United States, we encourage debate and discussion. And so for some of you from a cultural background where that is not encouraged, that may be a little bit of a struggle. And what I emphasize is that does not, very often it's confused with lack of respect. It's not lack of respect. Everyone will appreciate you here for debating and discussing ideas, and it can be done respectfully. You can respectfully say, you know, I have this idea, what do you think, and how we do. And if you have a good advisor and good colleagues, they will appreciate this, and they will actually like a healthy and good debate. So the goal is persuade and to market your ideas and contributions, and so don't be confusing, but just say it clearly. Keep them simple. So when you communicate, don't overload it. And what I always tell my students is make the problem, first of all, clear that you're trying to solve, and then explain it in very practical terms. You know, you have to imagine very often you're talking to scientists who very well have a good reputation, and but you have if you do research and you become really in-depth, working in depth in a particular area, very quickly you become the world's expert, and nobody else knows as much about that detail as you do, including your advisors, including computer science professors, etc. So don't embarrass them, you know, because if you can, and then they might be polite, etc. But, you know, engage in a good debate, explain it in practical terms. So that doesn't mean you have to treat other people as stupid, but if you explain to them at their level, you know, so that they understand where you're at or what you're trying to do, then you can engage in a really great discussion. And these are intelligent people, but not experts in your field. That's the point. So they should understand. Explain it in the way that an intelligent person in your field can understand, but someone who's not necessarily an expert in your angle of it, right? And that is a communication skill you really need to learn, because it makes the whole world of difference between your research really getting traction and not. Keep it well structured, explain the problem, explain the approach, explain the experiments, the results and the conclusions, and then repeat the main conclusions. Isolate the main points, omit unnecessary detail, and so on. Very often, students really are so engaged in the details that they miss the point of communicating the big picture. Public speaking, that's again back to the shyness. Many of you are shy, and speaking in front of a big audience doesn't come natural. It doesn't come natural to anyone. We all start shy. My first presentation on my first talk, I got a paper accepted back in my undergraduate days, and my very first talk was Kresge Auditorium. If you know MIT, it's the largest auditorium that MIT has. It was huge, and they had these spotlights, right? So I couldn't see the audience. You have these lights in your eyes, and you're supposed to focus on your speech. It was scary. And I'm telling you this, everybody does. And at some point, this is, of course, something that's frightening, and you need to learn it, and you need to practice it. And then if you add that English may be a foreign language for you, and you might be shy, doing this is complicated. So what's helpful to do that? Start in a friendly audience. You know, don't avoid, but seek opportunities to give little talks or talks on your research in your research team. Doing this in front of 5 or 10 people is easier than in front of 200 or 500. And practicing in that context with a friendly audience is obviously an easier way to get involved in this. And then, of course, the university also offers English speaking courses and writing courses. So if you feel you struggle with that, you know, take advantage of these offerings. Discussion, I said that before. Debating needs to be learned. It can be done polite. It's not a lack of respect, and it's encouraged. You know, nobody has perfect answers in research, It's an unknown open question you're looking at. And so seeking debate and discussion with others is in fact what we want and what you should seek, etc. And it can be done politely. It's not, often people think it's impolite to debate with your professor, but that's not true. You can do it respectfully, and they will appreciate. It's also a way of building social relationships with fellow scientists, publicize your ideas and contributions, and help the scientific community to progress. So for all those reasons, we go to conferences and we do that, and this debating is an important element of making progress. Writing is a very similar story. In your writing skill, you also have to learn how to do scientific writing. I keep in my garage here in Murraysville my first report that I ever wrote, just to remind me that this is not something that you know automatically. My first report was terrible. I shudder when I look at it, because you start writing in a very colloquial way and you don't know yet how to write scientifically, right? Because there's even jokes about how you write scientifically, right? About it is generally believed. It means, some of my friends think, and further research is needed means my results don't make sense. There's a whole joke page on the internet. You can look it up, but you need to learn how to sound like a scientist. But then the more important point is also to structure it in a way so that people will be engaged. Now, why do I say that? Because you can write a paper that is confusing in the title, confusing in the abstract, and people will stop. They will not. People are busy. And they get thousands of papers every year to read. And if you have some paper I have a relative who is in marketing, and he says that if you want to market a children's toy, you have to be able to explain what that toy does in 2 seconds, because people walk through the supermarket, and if they see that toy and they understand it in 2 seconds, they will buy it. If they don't understand it in 2 seconds, they will walk past and you lost it, right? So they will not buy from you, right? So your idea generation in research is similar. You have to engage people in the title already, then in the abstract, and then in the introduction. And only if you engage them and said them, this is really fascinating stuff, I want to know more, then they read the details of your experimentation, right? Otherwise, you lost them, and you lost the opportunity to have impact. So therefore, tell them what you're going to tell them, and tell them what you told them, right? So you repeat the story in some sense in different levels of granularity, and this is what the practice of writing skills will do, to give you a structure of how to publish papers and so on. And once again, if you struggle with that, practice it, do it with your advisor, get feedback, and then also consider taking English writing courses if English is in fact a struggle for you. Okay, I'm pushing my time limit here. Let me quickly go through funding. Funding, the money aspect is of course an important one too, and so I need to explain that also. Your support in the program is not free. It has to be paid, and typically by your advisor. Most of us, university tuitions and graduate stipends have become so expensive. I don't know, I think this number is old. We're now probably up to 100,000. Is it? What does a graduate student stipend cost per year, Graham? You should know.
With overhead, maybe year 100,000.
How much?
Close to 100.
Close to 100. $100,000. I mean, my mom couldn't have paid it, right? I mean, this is not possible. It used to be that you wash dishes over the summer and that carried you through education. That's not possible anymore. And you have here all the public discussions on student loans and so on. It's become a real problem. Now, with the way we handle this here typically is we get research grants, and so most of you, I would imagine, are on a research grant of your advisor, right? And so that means your advisor, I'm sure Graham has more stories and others. We all have to bust our butt to always write proposals and give presentations and so on to get money, right? Because it costs money. So it's tuition, stipend, overhead, travel, plus equipment. And the amount of money that it costs is comparable to a research programmer, right? So I can hire a staff member for the same money that it costs to fund you for a year. And if that's the case, somebody will want something in return, right? And who will pay for this? And the sponsors are typically companies, governments, and foundations. And the sponsors want to result in a return. Why are we attractive? Why do people do it? Because we do more innovative stuff, but it's on par with, they will have to decide in their company or in their government, do I hire a trained scientist to do this development for me, or do I give the same amount of money to Carnegie Mellon so that some propeller head can think deep thoughts and do something that may not be possible, right? Well, there is a trade-off there, and and there is a good reason we're still successful with it, but it means also for you as a student that you need to pull your share of the weight. So just getting all A's in courses, the sponsor will care less, and they will really want more something for their money, whether you get an A in course XYZ. You need at least a B to pass, but you don't really have to push so hard to get an A. Make sure you do some contributions on the research too, because that's what the sponsor will care about, and therefore your advisor too. So you will have to help secure your support by producing good research for sponsors, get results, systems, software, and performance, and then communicate the result. Here you have it again. If you don't tell anyone, nobody knows, and why should they pay for something that nobody knows, right? So that means also building demos, doing presentations, writing reports, doing software installations, and doing talks and discussions. So it's a whole package, and as you will see, it's actually not, some of you may think it's a horrible chore, but yeah, the reports are chores usually. But the rest of it is actually fun because you really meet interesting people and you learn from it a great deal too. So your advisor advises you, right? We're not talking about a boss, right? Advisor is someone who advises you, and that, remember, this is research. Nobody has a perfect answer. There are no known solution, and there's no right solution. So that means don't expect the advisor to tell you every day what to do next. There is some guidance, yes, but it's give and take. And so you do this interactively in a dialogue with your advisor who has some experience advantage over you, but in the end will also appreciate that discussion and the insights you bring. So your research is valued ultimately by the impact you have in the international research community, and not because the advisor likes that you did something. You're not making tea for the advisor, right? So it's just what the advisor does is guide you and help you try to succeed as a researcher in the international community. And the evaluation metric is whether your ideas and your work actually succeeds in the international community, right? It's different. So we're advisors and not bosses. Okay, so there's a whole list of things what an advisor is. Maybe he or she has hunches of possible things to try, help define and guide towards useful problems, have a historic perspective, so you don't make the same mistakes that are already known, and has maybe a gut feeling, this understanding thing that they may have, but be careful with that. Sometimes that gut feeling comes from too much history, and a fresh approach is good, and we welcome that too. Help the scientific taste, whatever that means, and the advisor helps you raise funding, and very important, advisor, he or she produces also connections with the research community, introductions in the research community, introductions with sponsors, and potential employers for later. Okay, I know I'm already over time, am I not?
So we have, this is till 45 past, and that's in 5 minutes. So if you want to take questions, you could take 5 minutes.
All right, then let me wrap this up in really quick in 2 slides. I think one thing I want to still make as a point is when you're choosing advisors, there's also different styles. There are big projects and there are small projects. In every department you find people who run enormous projects, and then some people who are much more focused on a narrow element, and that's a question of where you feel comfortable. Some people, big projects are, have excitement, there's usually money, there is work with a many team of experts. There's opportunities to have impact and do great challenging things. And the advisor may have good connections, but the advisor is usually on travel and gone and doing something. So getting time in that case is a disadvantage. And in a small project, it's the other way around. You usually get much more personal attention, sometimes more weekly feedback, but it's generally a smaller problem. And then the potential for impact may be different, and it's less of a team effort. So, and occasionally resource limitations maybe, right? So seeing where you feel that's a personal choice. You know, wherever you feel comfortable, you need to find your way where you think you might feel more comfortable, because we have that both. I know I'm not supposed to be marriage. We used to call it marriage, but it's now called matching. I'm sorry, blank that out, erase from the video. But it's this process we do of where students and advisors meet each other, right? And it's not in one direction. You choose, they choose, and in so doing, you pick based on your preferences what is interesting, what is fundable, because you need the money. Do you like the person, the advisor as a person? Do I like working in a team or by myself, a big project, large project? Can I work independently, proactively, or do I prefer weekly attention? Can I contribute usefully to the advisor's research? So these are questions you may want to ask yourself in your choice of an advisor. As I said, it's an 80-hour week, 50% research, 50% courses. And so you need to also do how to cope. You know, how do you do that? Coursework is immediate. Research is usually long-term, and that causes a tendency for students to focus on the coursework because there's a weekly deadline. In your research, there isn't. Don't make that mistake. Let me make that very clear. You don't want to go through a whole semester and find out you did nothing in research, but you got A's in all your courses. Then you will be reviewed badly because you didn't make progress on the research side. And that means scheduling and planning your time or managing your time correctly. And my general recommendation is do like this. Take the time between semesters and focus on research very actively. Then prepare the next semester so that when the courses are still light, prepare your experimentation, your discussion, and so on, so that when the courses become more intense towards the end of the semester, you can keep pretending to your advisor that you're continuing doing research because you just keep the machines running and you report new results. But to set up the machine so that you can pretend, you have to make sure you work hard in the beginning so that you have results cranking out every week at the end anyway, right? And so that's a time management skill, because it is, of course, true that you can't do 50-50 all throughout. The courses become more intense, so doing this time management is important. All right, so that's the phases of a PhD are excitement, fun, panic, and then the low point syndrome, what I call it. What does that mean? Initially, you're excited, then it's fun, then you panic because you need to do your thesis proposal, and then comes a low point syndrome. You've been here so long. Remember that. When you get 1 year before your PhD, you will have that low point syndrome where you say, I've been here so long, I got to get out of here. But my PhD is still not in sight. I still have so much to do. But it's too late to quit because I spent so much time on it already. So many students get depressed during that time, and different personalities. But make sure you remember everyone's been through it, and then plow through it and don't get discouraged. You know, work towards the finishing line and get your PhD done. And don't forget that research is a chance to explore new frontiers, mysteries, and puzzles. And most of all, it's a chance to have fun. Okay, thank you.